Good morning. I hope you're all well as you watch this video. Um, Real quick, last week I had you watch a movie, which I hope you enjoyed, but it was just about the history of the Earth from before it existed all the way to today. And now we're going to look a little bit more into the specifics of what you saw during that movie. It included a lot, including earth science. There's a lot of biology in there, which I'm not necessarily concerned that you know very well in this class. But we're going to spend the next couple of weeks going over what I do want to make sure you know very well. First, starting with continental drift, which is how Earth got its shape in the way that we see it today. As always, first we'll go over objectives and what you'll be tested on. You need to be able to define plate tectonic theory and thermal convection, so those two different things. Explain the relationship to thermal convection and plate tectonic theory. Say that 5 times fast. Use plate tectonic theory to predict how continents will look as plates continue to move over time. So those 3 things are what you will be tested on for this topic. Before we talk about plate tectonic theory, we need to look at the structure of the Earth. So if you could slice a piece of the Earth in half and just look at that outer ring, hope that made sense. This is what we would see. So this is just that first top layer of Earth. As we know, the Earth has 3 main layers, the crust, mantle, and core, which is likely what you learned in previous classes, maybe in middle school. The lithosphere, though, we're going to break down these pieces into smaller bits and more specific parts. The lithosphere includes the crust and the upper part of the mantle. Let me just draw you a little diagram here. So if we have Earth, this first layer is the crust. It's very uneven. Then we have the mantle. And then we have an iron core. And we're going to color this mantle in. I really need like a Surface Pro or like a little tablet with a pen. I feel like that would make my life so much easier. Okay, but that'll do for now. The lithosphere is going to include the crust and upper part of the mantle, which is, this is the crust and this is the upper part of the mantle. So this section here is the lithosphere. And we're just going to abbreviate that as lit. Lit, okay? The lithosphere is a firm, rigid layer which sits on top of the asthenosphere. So the asthenosphere is going to be the bottom part of the mantle. Ooh, that's really bad. A-S-T will be asthenosphere. The asthenosphere is the lower part of the mantle. It is made of rocks near their melting point, so it's softer and it moves. So this part, it's soft, it's flowy, it's molten rock. It's not quite a liquid, it's not quite a solid either though. It's kind of like a putty, if you could imagine that. And then we have our crust and upper part of the mantle here. We have continental crust, we have oceanic crust, but it's all crust. This part is firm and rigid. So it's kind of like a plate. If you could imagine, I don't know if I have a good mental picture. I'm going to keep thinking about that. But basically we have this firm layer sitting on top of a soft layer. So that allows the firm layer to kind of move around, drift around this top part. The way that happens is called thermal convection. This is the process of heat causing parts of the mantle to rise, cool, and fall. This process is going to force the lithosphere to move. And I'll show you what I mean. So the core of the Earth would be down here, if we're looking at this same image. And the core is the hottest part. So this bottom part of the mantle is going to be hotter than up here on this top part of our asthenosphere. We know that heat causes things to rise, and this is true in this case too. So this bottom part is going to rise, causing that molten rock to move upwards. And as it sits towards the top, it's going to start to cool down and fall back down. And this is just a cycle that will keep repeating. This is called thermal convection. Thermal meaning heat, and convection referring to this circular motion. And as you can see, as this thermal convection occurs, it's going to force our lithosphere to move. In this case, it's being moved downward and it's being forced under this bit of lithosphere. And this would form what we call a trench. But we'll look more about that next week in actually how mountains, volcanoes, and trenches form. So this is basically it. On this side, maybe our thermal convection is going in the opposite direction. And that's going to force this lithosphere to move this way. There's cycles like this all over the Earth, and that's going to move its respective plates. Moving on, this is tectonic plate theory, or plate tectonic theory. This theory states that the Earth's lithosphere is divided into separate plates that move independently of each other, meaning all by themselves, due to thermal convection. That's how the two connect. As with any scientific theory, there is a wealth of evidence that supports it. This is a common misconception that theories are unproven or that theories are less than a law in science, and that's not the case at all. A law is actually going to highlight a relationship that can be shown mathematically. So gas law, for example, states that as you increase the pressure of a system, that the volume of those gases will decrease. That's just an example of a law. A theory is not going to have that mathematical relationship, but it is going to have a wealth of evidence. So lots of evidence that supports this theory. And then this picture here is just showing each continental plate. You'll notice that it actually does include the ocean. So it's not necessarily that our continents are moving on their own, like on top of the ocean. That's another common misconception. This whole piece of ocean and land combo is going to be moving together as a plate. Same with this one, and this one, and so on. So yeah. Here's some evidence, and this is just going to be really brief. I have this name here, Alfred Wegener. I think that's how you say his last name. He is a scientist that is credited for coming up with this theory and actually finding the evidence to support it. So lots of people notice that our continents kind of fit together like puzzles, but this guy is the one who really took the time to find the evidence and kind of say, hey, this is real, this is a real thing. So the first piece of evidence is the one I just mentioned, the continental jigsaw puzzle. Many scientists observed the similarities between coastlines on opposite sides of the Atlantic Ocean. So you'll notice that South America looks like it fits right into Africa here. And here are the others. I don't know why this is the one that stands out the most to me, but it does. Fossils matching across the seas is another piece of evidence. Some types of land connections was needed to explain the existence of similar Mesozoic age life forms on separate continents. So scientists notice, hey, we have some, I can't quite read this, let's just call it an ancient lizard. We have some ancient lizard fossils here in South America, and we have them here in Africa. And it's the same species. So the only way that this species must exist on different continents in this clear band pattern is that these continents were once connected. And that allowed that species to live during that time. This lets us know how long ago that these continents were connected. You can get a lot of information. Same with plant fossils that kind of go across Australia, Antarctica, South America, and Africa. It's just, again, it's a clear band, which suggests that there was a time that these were all connected. It's not like it's scattered over here and over here and over here. No, that was supposed to be an X. It's clear what's happening. Let me erase that because I think it's a little distracting. Okay. Another piece of evidence, I think this is the last one, is that rock types and geologic features are going to be the same across continents. So not only are fossils going to coincide, but Wegner found that 2.2 billion year old rocks in Brazil. Brazil's around here. Those match similarly aged rocks in Africa. So based on this picture, they would probably be around there. If we have the same rock types, that suggests that those rocks were formed in the same way during the same time, which means they must have been in the same place. That's the logic we're working with here. We also notice that mountain range of comparable age across continents are along the Atlantic Ocean match as well. And I can't spell, I should say as well. So we have the Appalachian Mountains here along our east coast, and these match up with the mountain range in Greenland and across Scandinavia and the British Isles and the west coast of Africa. So all these mountain ranges look to be about the same age. They have about the same composition. This lets us know that these ones were the same mountain range, and they have just been torn apart by this plate tectonic. Okay, so this is an excellent example of scientific method in the scientific community. This is a big deal. This is a big theory. I'm going to have you guys click and learn more about this theory and the scientific method here. So just go ahead and click that link, and there will be a quiz posted later this week on this topic. Remember your objectives. That's what you'll be tested on. You can go back to the beginning of the video in case you missed those. But other than that, I will see y'all next time.